Um, I'm Prithviraj, or I also go by Raj. I am an assistant professor at University of California, San Diego, and also a research scientist at Databricks. I was previously with Mosaic before we got acquired. So I have two jobs. I do two full-time jobs effectively. And I usually take my coffee black, but with sugar. So usually like no cream, but we'll have some amount of sugar in it.
Welcome back to the MLOps Community Podcast. I'm your host, Demetrios, and today talking with Raj all about fine tuning, but not just any kind of fine tuning. We're talking about Tao fine tuning, the method that he came up with and wrote an incredible blog post about. Why don't we just start this conversation? Do you call it the Tao? Do you call it Tao? Or do you call it Tao?
Yeah, we're just gonna call it Tao. It's gone through multiple naming changes internally. Tao is actually the final version, which is what ended up sticking. That we came up with like maybe a day before the blog post went live. Um, so
That's
internally, it's
already
actually key to something else in my head. Because for the majority of the time we were thinking about it as a different name, but we decided that this was a better name overall.
because whenever I see spelling like that, I always think of like the Tao Te Ching, you know?
Yeah,
And
yeah. I think they were just we were just thinking like cow. Yeah,
Tao is perfect. So,
yeah.
what is it?
So Tao is basically at a high level a way of people fine tuning their own models for their own domains. Right. So there's always been this sort of like stress between, well, do you have one model to rule them all? Or do you have, a sort of a separate model for every single individual domain? And given that a lot of people's data is private, we kind of seem to be gravitating towards a world in which these aren't actually necessarily like entirely orthogonal, but they're very much in a world where a lot of people do need customized models for their data and their use cases. And so that's what it is. It's a way of doing that. And most importantly, it's a way of doing that without people having labels, right? So like the bane of every single machine learning person trying to build a custom model is like, oh no, where am I going to get the labels for this data? Right. The
Expensive. So
Yeah, these are
expensive.
expensive. The annotation costs are gonna be super expensive, and we've heard this, like, time and time again from, so many customers, right? Like, that's actually where some of the initial motivation came from, right? So we were thinking, okay, well, the initial version was like, okay, well, what would it take to have some kind of a system where people are deploying their models, collecting feedback in some form with these models, and then using those to continuously like improve them through time, right? Um, but not everyone has access to be able to like collect this sort of like feedback and whatnot in real time. And a lot of people just straight up, they have like an idea of the tasks they want to do, right? They have some prompts and whatnot, but they don't have a particularly like large data set on how to do it.
And so the basic there was okay, you don't have a large data set. You also don't have a very labeled data set, or you don't have any labels because it
Yeah.
takes a lot of time and effort to create those labels. So, how can we still get something of value without any of that?
Yeah, and it's a little bit like counterintuitive from like all the classical machines, like supervised learning perspectives, right? It's like, oh, we're taught like, always think really hard about your data, right? You need like good data. And then if you think about how like a lot of the big companies are making their models too, right? Like they do have a ton of like human annotated data. Um, right. So that was like the sort of like initial key challenge that we spent a lot of time like brainstorming through is like, okay, well, if the way to get people to use something like this, right? Like this RL, like XF as a service. And so like I'll get to I'll talk about the RL bits like later, but basically this sort of like continuously improving like domain specific specialized models thing, then we need to like make the barrier to entry as small as possible.
That's funny. Anybody that has taken the Andrew Yang course is like, "You can't do that. No, it's all about the data. What are you talking about? No labeled
Yeah.
data?"
Yeah. Well, it turns out that like it kind of still is about the data. It's just like we abstract a lot of it away for you.
Okay, tell me more about that.
And the data is like it's synthetically generated under the hood, so to speak. And it's synthetically generated from the model itself, right? So here's the way I like to think about it, right? So the way we do this is very reinforcement learning based, and the way I like to teach reinforcement learning usually is you think of this as like personalized supervised learning for the model, right? Um, where if you do normal supervised learning, you just have like a ton of labels that a human has kind of annotated, and you're trying to learn how to mimic the human's labels or whatever. Whereas in the reinforcement learning case, the model is itself generating data, right? The model is making these generations. So you have a prompt. The model like generates like one or n responses for this particular like prompt, and then it gets feedback. It's like, okay, which one of these things was good, which one of these things was not, and then it tries to learn from that, right? And so it's learning from its own mistakes um, here, right? So it's whereas like if you were training it entirely on like a human data, it would be learning from a human's mistakes. And the key aspect of this is uh the mistakes that like models make when they're like reasoning about something is different than like how humans do it. So it actually turns out that in like a lot of cases, the human data is not necessarily gold truth. And so that's probably like one of the key reasons this actually like works is being able to have these models like learn from their own mistakes in like a way that's specialized for the models.
Okay. So break down exactly how this is working and what, because it's all, I think we jumped into it saying Tao, the Tao stands for something, right? And it's not the land of 10,000 things. It is test time adaptive optimization.
Yeah. So I guess at a higher level, right? So it's actually very much the process that I was just explaining. So people will come and they have like a bunch of prompts, right? So that's the barrier to entry now. Some customer comes and they say, "Hey, we have these tasks. These are like the types of prompts that we want to give this model." And then what we do is we take those prompts. Internally, we have these like our like base models. These sort of like up to some extent pre-trained LLMs or whatnot. We have them generate a bunch of responses from the model, right? So there's various sorts of techniques on how to do this, but the general gist they all boil down to is you are trying to generate different responses, and then we have another model which is called a reward model. Um, and this is pretty important. So what we have, this reward model will take these like responses that your generating model, right? This like which I'm gonna call a policy from here on out to try to use more like RL language. This reward model is going to take the responses that this policy has outputted and then score them, right? It's going to be like, this is, +1, plus zero point 0.5, -1, minus zero point 0.5, right? Um, and then via reinforcement learning, we can then train this policy to say, okay, well, some of these responses were really good, right? And so, because these responses were really good, we're going to change the weights of the model to upweight those, right? To make it more likely to produce outputs that are like the ones that have high scores,
Yeah.
and make the model less likely to produce outputs that are like the ones that have received low scores, right? And then that process sort of like repeats iteratively.
Which until now is standard reinforcement learning, right?
So this is mostly like standard reinforcement learning, right? What I've described. The key things that we've had to do in this particular case is, well, one, if you think about it, this like reward model that we have is kind of providing labels, right? And it's doing a lot of the job of like ranking these like, inputs and out like these outputs of the policy. Right. It's giving some kinds of like scores. And so it's really important to have a reward model that is trained really well across like a wide range of tasks.
Yeah.
Um, and so that's like one of the things that we talk about in the blog post. We have this like reward model called like a DB reward, DBRM. So like a very enterprise focused reward model that's able to judge tasks across a wide variety of possibilities. So the reason that this is simpler is that it is easier to train models um, to judge whether something is correct or not, as opposed to actually trying to come up with the correct answer yourself, right? So this is this like verification problem, and so the verification problem is easier than the generation problem, usually
And cheaper.
speaking, and
Yeah.
cheaper, right? And so we spent a lot of effort, like gathering the data to make as like wide ranging and generic a reward model as we possibly could. And then for the vast majority of use cases, at least everything that like we've shown in the blog post, we use the same reward model across like, text to SQL, across like, finance bench, which is like
Yeah.
like the finance domain question answering kind of thing. It's actually the same reward model. It turns out that same reward model is able to judge outputs for like all of those tasks.
And the
That
reward
that
model was a fine-tuned model that it was like some llama base or something that was fine-tuned, or it was a completely separate, smaller model?
It was like another model that has that was like a base. So think like, in the Llama style, or like something like open source style Llama, DVRX, whatever style like base model that we then like fine tune on top of. So the conventional wisdom for training reward models is like you usually do start with like a pre-trained and then like somewhat like instruction tuned model, and then you add like an additional like head on top. So instead of like mapping to this, giving you logits, a probability distribution across your entire vocabulary to figure out what token to predict next, it's giving you a single scalar value now.
Yeah, okay. Now, the other piece that I wasn't super clear on here was that you're saying the reward model is basically giving you, if you squint, some annotated data.
Kind of. It's very sparse annotated data, right? So it's feedback data effectively. So um, the reason this is like possible is, so let's look at this in terms of like information density, right? So if you have like pure, like imitation learning data, right? Supervised fine tuning, like sort of data where, you have to have a human write down exactly how to do a task, right? Exactly like all of the outputs for how to do a particular task given like the input prompt. Um, that's very information dense. Um,
Yeah.
Whereas the information that this model is giving it is like, okay, you're generating this entire like sequence. After the entire sequence or at like breakpoints in between the sequence, we're just giving you like a scalar value,
Okay.
right? At sort of like, predefined like breakpoint. So it's a lot less bits of information that it needs to be able to predict. And so that problem is easier.
So now where does the test time annotation come in? I feel like,
Yes.
yeah, there's another part to this story that
So the other part to this story is that, okay, well, so you have like the reward that's like scoring stuff, right? But what's it actually scoring? Um, right? And what it's actually scoring is what's on the policy side. So the policy is generating like responses, and the policy is generating, and you can generate one response and score that one response, right? And then learn from that. You can generate two responses and score that. And then the way you do it is also like important, right? You can condition the second response that you generated based on the first one, right? It's like, okay, generate something different from what I like generated the first time around, or whatever. But if you think about it, that is inference time compute that's being used.
yeah.
The more types of responses that you're using, the more types of responses you're generating, the more test time compute, so to speak, is actually being used here. Now, the terminology is it can get like a little bit confusing here, and the reason we used like call up this like test time compute is this test time compute is just the model during training. Um, Using additional inference time compute, right? Um, but once this like whole training process is done, and then the model's like actually like deployed, um, it doesn't do multiple response generation or whatever, right? And so the inference cost for the actual user is the same. We are eating up a lot of the inference cost during the training process.
I see.
The additional like adaptive test time, like that bit, um, is eaten up during like kind of ahead of time, so that like when it's actually deployed, um, you can kind of expect the same, like inference latencies and whatnot.
Yeah. So it's not like a deep research or whatever R1 reasoning model where you're gonna give it a prompt and then come back 15 minutes later. It is doing that test time compute at the training level as
Yeah.
opposed
So
to
the process would go, right, like customer comes, they have like a bunch of prompts that they give us, um, and then we would do this kind of like like reasoning process at training time, and so we would just like drop it in and then come back a couple days later, right, or like whatever amount of test time compute um, that we want to use for this particular task. Um, these responses all get like scored in various ways. And it turns out like how you generate the responses like also matters, right? So there's like very popular techniques like best of n, which is you just kind of like generate n different responses, all IID, right? Independently sampled from each other. Turns out that's like probably not the greatest idea, right? Is like you're actually burning a lot of like redundant compute. It works, but in terms of like trying to be at least somewhat more compute efficient, it gets like a little bit redundant, right? So if your underlying model doesn't have like very much diversity in the range of things that it can say, then if you generate like n responses, it'll turn out that like k subset of those n responses will be just very similar to each other, and you've just burnt a bunch of, and like the scores for those will all be the same, and there's no additional learning signal to be had in just trying the same thing over and over again. So you have to be a little bit smart about how you actually do this kind of sampling, and that's like one of the things that we like internally developed is like being smart about this.
Because it it's not the amount of ones, or I guess to put that differently, you quickly realize that if you're scoring the same thing, basically it's the same words, but or it's the same idea and different words. And so it's getting the same score, and that's not adding any richness to that base model.
Yeah, you're not like extracting any like new information, right? From like an information perspective, you're kind of like dead in the water. So you have to be like careful about how these responses are generated in the first place, right? And how you're doing this like exploration from the RL perspective, such that the feedback that's given by the reward model is actually useful.
Mhm.
Um,
I was figuring you were just gonna turn the temperature up to 11 and then see what happens.
we did try that. That was actually probably one of the first things we tried, is like, okay, let's just turn the temperature up and see. But it turns out that doesn't like work particularly like well. It kind of depends on the use cases. So like if you turn up the temperature really high, it's like actually, if you're doing like creative writing, right? If you want like character AI sort of like chatbots, it could work. If you're trying to do like enterprise things, you probably don't really want like that level of like super high temperature stochasticity. So you have to do things like you have to like be able to like condition on previous responses. You have to make sure that like you have some definition of like, if you have one response and you have like another response, you have to have like a definition of like how close or far apart from those two like from each other they are, and then make sure that the next responses that you generate are sufficiently different from all the previous responses that you've generated.
Have you tried to do this over and over, and do you see, like, loss from when you've done it, like, 2 or 3 times? Because I can imagine a world where you say, "Alright, cool, let's just set up a retraining pipeline that kicks off every week or every couple days or every month," whatever it may be, but then you start to see almost like compression loss in a way?
Yeah, yeah, that's a great question. So, like the answer to most things in ML land, it depends. Um, Right. And so I'll tell you cases it works and sort of some cases where it's not so great, right? So it turns out that actually like one of the things that we did in Tao is we just kind of like ran this process sort of like iteratively more and more, and we're like, oh, damn, the number's just going straight up. Right? Like
Best
it
graph
just
ever.
keeps, yeah, this is the best graph ever. It's just going up and to the right, like just
Yeah.
continuously. Like this just keeps working. Um, and this was like a year and a half ago. At this point, we're like, this is great. Our reward model works, like all of this works. Um, but it turns out there's two things that could go wrong here, right? One is this like obvious issue, or in hindsight, obvious issue of reward hacking, where it turns out that like your reward model is not entirely like 100% accurate, right? There's some amount of like noise in it. And so if you spend too much like compute, and you're just doing this like looping around, at some point you've extracted all of the useful signal from the reward model, and now you're kind of just learning the remaining like error noise.
Uh,
Um, right.
oh,
And
interesting.
this is, like I don't know what overfitting really means anymore. But in like for a classically trained ML person, this would be the way to think of it is like this would be like an RL-ish version possibly of overfitting, where you're really good at optimizing for the reward for a particular like model. But because that itself is just a proxy for what like a customer or someone might want at the end, it what doesn't really do so well downstream.
It's almost like I think about when you're squeezing a lime, and in the beginning you get all that juice, and then later you're like trying to squeeze, 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 and it's so much effort just for like one drop. And
Yeah.
really, it would be even
And
better if,
like it yeah, and it starts getting bitter too, like,
yeah,
if you start squeezing at the end, right? Like, and like it's somewhat well known, but it's really interesting to kind of see it in practice, and it's like a very much like a somewhat of an art to figure out like, oh, what is that tolerance threshold, right? What is that cutoff, and how do you get that cutoff in like a generic way, such that multiple different customers can use a singular reward model. Um,
because, well, what would you do then? Do you just swap out the base model and like start over from zero again, or how do you?
well, I mean, you have checkpoints from like sort of like all through the training process, right? So you could roll back to a previous checkpoint. Like ideally, like the way this would work, right? The ideal loop of what this is would be, you have some kind of like generating model that burns like a bunch of inference compute, and simultaneously you have this like reward model that's trained, and then at some point you cut it off, you just deploy the model, and then you collect new feedback
Yeah.
so that you can actually like update your reward model, and therefore now there's more signal in the reward model, and now that there's more signal in the reward model, right, you can now train again on it, right? That would be the ideal loop. Is you're doing this like cycle of like redeployment, and this is what you were talking about, right? This like redeployment thing and like retraining across like deployments only works really if you are able to get new signal in between each, right?
So if
And
it's
that
the
new
same
signal,
questions, yeah, I get it. Yeah.
if it's the same questions, right, and you've kind of optimized up to a certain extent already, you're not going to get anything like more after these sort of like initial training run, because we're already doing like a lot of that like optimization for you, and like we're figuring out dynamically like what those like thresholds and stuff are. So like ideally, right, if somebody comes to us and they're like, okay, so we have these prompts, this is cool. We will then use this like, like Tao method overall, figure out like, all these sorts of like thresholds, optimize against this reward model that we have dynamically. Um, and then we'll give you, and like, the model goes back to them, right? Uh, the reason you would want to then like retrain it like further would be actually, you know, we have these new tasks now that we want the model to be able to do. Here's a bunch of new prompts. And we are reasonably confident that these new prompts are actually doing something different from the old prompts. And to use your own words, they're not like the same thing, but in different words, because we kind of count for that too, sort of under the hood, of like taking your prompt data set and then just making sure we're covering all our bases of like, oh, here's like all the ways that like people could possibly say, or ask for these like same set of prompts. Um, yeah. And then so if you have like a bunch of new tasks that you're reasonably certain is like different from the capabilities that the model has already like been trained for, then you come back to us and say, okay, well, we would like to optimize again, please. And then you do it. Right. And that would be the reason to retrain the model.
So what are some of the results that you saw when you did this? Like compared against different ways of fine tuning, I guess would be the main thing. And most of the time, right? And I'm sure you've seen this a lot. It's just try and optimize the prompts, try and prompt tune it to the best of your ability because you get such a fast feedback loop. And then
Yeah.
if you can't do that, then figure out if you need to go and you need to fine tune and then what kind of fine tuning with how many. GPUs and all that, what data, what labels, all of that fun
Yeah.
stuff. There's so much of a headache that comes along with fine tuning and not doing it right. And then later, after you fine tuned, you realize the model actually performs worse. What's going on? And so here I see the value prop really clearly. You say, look, the labeled data you don't need to worry about, and we'll actually just give us your prompts and we'll make a model that works better on these prompts.
Yeah, yeah. So again, the standard machine learning like adage of there's no free lunch is very much true, right? So these prompts can be from like multiple different tasks. And we can make your model better at these like multiple different tasks, but you're trading off performance somewhere else. Right. So like you're like, like most of the customers will come to us, they'll have like a bunch of like enterprise based like prompts, but you're probably, like reducing the model's like underlying creative writing, right? But that's
Which they
fine.
may
They
or may
don't
not
really
care about.
yeah,
Yeah,
which they like probably don't really care about, right? And if they do care about it, they can come back to us with like creative writing prompts as part of it, and then we can optimize for that too.
yeah.
Um, right.
Give me my financial statements in the style of a Bob Dylan song.
Yeah, exactly. That'd be cool actually. Um Yeah, maybe I should figure out ways of
Making
teaching
that happen.
students that way.
But
Yeah, yeah.
the other thing that just popped up there, in my head as you were saying that is, do you need a certain amount of diverse prompts, or does it perform better if you give it a much bigger set of prompts? Because you were saying at the end of the day, all of the output that gets scored, you reach that threshold. So in my mind, I'm wondering, oh, well, if the input is more vast, then does that mean that you can get more out on the other side? And I'm sure you looked at that.
Yes. We absolutely did look at that. I guess the high level here is that like it is absolutely true that the bigger your prompt data set and the more diverse your prompt data set, the better the performance is going to be. And for the longest time, actually, we only found that we were able to get like good performance. At least good performance means like we could train like a relatively small parameter count model to match the performance of like 4.0 or something on a particular task if we had like a really big prompt set, like a really big diverse sort of a prompt set. But
And really
if
big
you
is
think,
like 1,000, or
yeah,
it's
big
like
would be in
5.
like in the thousands,
Okay.
right? But that's a pretty big barrier to entry again, right? If we're like asking for like no labels, but we're like, okay, only prompts. But actually the asterisk is that like you have to give us like, 10,000 prompts or whatever. That's a pretty big barrier to entry. And so we don't require that. We found a way around that. Basically, such that for the sort of like end customer, they can give us just like a subsample of the kind of range of things that they think the model can be used for. Um, and then we'll take it from there. And we'll figure out how to like, get that kind of like, diverse like prompt set or whatever, and learn from it.
Yeah. So it's like I come to you with my 3 prompts and you're like,
Well,
"Don't
hopefully you
worry,
have
I'm
more
gonna."
than 3, but, like,
You
there's
gotta
probably
work.
some yeah, but, like, if you come to me with, like, only 3 prompts, like, we would do a great job, of that'd make our life easy. Is like, I just need it to do well on, like, these 3 types of prompts. I was like, "Okay, sure." Um, right? But, we'd be okay with, like, that range, right? It's like, oh, like, you know, 10 to 50 prompts even. Right? Like that range of stuff, and then, we can go from there, and internally, like, get to the stage where, um, we see, like, prompts that are a lot more along this line, and, much bigger sort of, like, data set, much more diverse data set, so on and so forth.
And so, the thing that is also fascinating here is that you were able to get such high performance from small models. And I wonder if you had no real constraints on how you were to do it, but I just told you, hey, smallest model, best performance, highest accuracy on X amount of tasks. How would you go about it? And it can be anything from, all right, I'm going to distill this model and then I'm going to fine tune it and then I'm going to, whatever you want. Like, how would you look at that and try? Or is it not even worth the headache of doing all these extra hoops that you jump through and you just say, I'm going to do Tao and it's going to be good enough?
I actually think like I'm gonna do Tao and it's probably gonna be good enough because like I think we've done a pretty good job of like figuring out what the sort of like optimal scenario is, even given kind of like all of these constraints, right? So these constraints are like fairly realistic. Um, but under the hood, we're kind of like relatively unconstrained, right? We have no compute constraints and things like that under the hood. And so like I think we've done a good job of like being unconstrained as much as we can on our side, whereas still accepting constraints and making sure that the customers are like don't have like a particularly high barrier to entry.
Okay.
Um, yeah, so I actually wouldn't change too much. Honestly, I think like if I'm thinking about it, if you're like, oh, you're like fully unconstrained, how would I do it? That's actually kind of the question I asked myself. And because that's what would be ideal, right? It's like, oh, because I guess the worst feeling would be like, oh, like somebody will come to you and they'll be like, oh, okay, well, you know, we have this particular task, like, we want to train models on this task or whatever. And then we're like, okay, here's this model that like kind of works asterisk. Right. But if we were more unconstrained, it would do better, right? And it's like that's a scenario I wanted to avoid.
Yeah. Yeah. Yeah, I hear you. So the other interesting piece here is, all right, does the how small of a model can you get to do how great of things, or how good can you get these small models?
Yeah, yeah. And again, it's a no free lunch question, but it turns out that like the smaller models, like the sort of like 8B range of stuff, you can get them to do pretty darned impressive things.
Uh-huh.
Um, right? And again, it really depends on the difficulties of the actual like tasks that people are trying to do. But what we found is that like in a narrow range, if you like take away its like broad intelligence and specify it for like, sort of more narrow data intelligence, so to speak, the small models are actually perfectly fine. The relatively smaller models. Right. So there's like a threshold at which they're like, good enough. Um, Now, obviously, like, you might be like, oh, like Raj, does that mean you don't believe in scaling? That's like, that's not true. I do believe in scaling. Right. I just like scaling is like an axis that, the more complicated a task you have, the bigger the model that you will need, in order to be able to like achieve it. Um, but not everyone needs so, like, you see the new Llama 4s, right? The behemoth, is 2 trillion, parameters, only a fraction of that are active, but that's still going to be, like, a massive pain to deploy for, like, the vast majority of people,
Yeah, people are
right?
not
Most
stoked.
people are not stoked about the size of the behemoth. Even, like, Scout is, like, relatively, like, large, right?
Yeah, and the
Compared to
performance is
Yeah, so, like, like, people have these kinds of, like, like, cost, quality, like, trade-offs, and every single customer, I guess, like, lies somewhere different on that Pareto frontier. of cost quality. And so when you're thinking about setting up any sort of a product where you're trying to like get people to make their own customized models, um, like things like, adaptive compute or whatnot are great because they basically like allow them to control where on the cost quality like frontier they are. Um, it's like, oh, spend more cost, burn more compute during training, get better quality at the end.
Yeah. Yeah. That's a great point is how, okay, you may need to optimize for a certain place in this whole life cycle. On you're okay with spending a little bit more money on that training to fine tune because later it means now you have that small model. And I imagine, have you played around with trying to like compress these models or distill these models even more to make them even smaller?
We haven't like yes, internally, like we've played around a little bit of like distilling it down from like the 8B size even further. And you can like still do pretty reasonably well for certain tasks on those. Um, but you start seeing like pretty sharp drop-offs if you're like doing like a 3B, like a 1B or like a 3B sort of a model. Even for some of the benchmarks that we were like thinking of or that we showed in the blog post, like the text to SQL, like Bird SQL and whatnot. Um, the drop-offs were pretty high, but for some of the other benchmarks, it worked okay. Right. So I guess it's like again, it kind of depends a little bit on how much or like how difficult the task is. But my impression is that the difference between 3B and 8B in terms of performance is disproportionately high compared to the cost difference,
Oh wow, okay. Huh. Yeah.
which is kind of why we presented a lot of results at the 8B scale. Right? So it's like, oh, it was not a linear correlation. Like the performance dropped off a lot more than like, say like, 3/8 of the compute or whatever.
Yeah. And the cost wasn't outrageously different.
Yeah, the cost isn't like outrageously different between like a 3B and like an 8B. Um, like right. Now of course there's like all sorts of like inference things that you can do. You can do like multi-tenant serving, like all that kind of jazz. But like we felt that this was like a reasonable trade-off. Like an 8B was like a reasonable trade-off. Um that is like still like fast and lightweight enough to deploy in like a lot of scenarios. But it's still able to perform pretty well, right? And the beautiful thing about Tao is that it just work like it's size independent, right? Like we have results on like 70B, we have results like internally on like 405B. And it just keeps working even better and better. Like
Did you notice any drastic differences or notable differences, maybe not drastic, between the models that you were using to fine tune on, and some took better to this method than others?
yes, kind of. So it really boils down to the models being able to generate diverse responses. Um, so there are certain models that are out there that have kind of been RLHF'd to death. Right. And so okay. So like from like my primary field of research is like RL. And so like what is RLHF really doing here? So kind of underneath, right? If you have some kind of like distribution, so the pre-training lets you learn all these like token distributions over the entire like internet language distribution. Um, like supervised fine tuning like makes that distribution like smaller, right? It's like, okay, well, I'm going to bias you towards this like range of instructions that I think the model is most likely to hear people like say to it and interact with it. um Now, like RLHF, there's been like a lot of sort of contemporary work that's been out in the open, which it shows that it makes these probability distributions super spiky, right? It's like instead of now being able to generate like a wide range of responses, you are now super constrained, right? You like can only say like one thing, and this is why you get all these like responses of like the safety types of responses. Like I can't do that for you,
Yeah.
right? Like it's kind of been beaten out the model. Um, that's not great from the perspective of doing further like optimization um, with like RL, right? So if you have like a a a reward, like I was saying, right? Like a lot depends on being able to extract good training signal from this like really great reward model that we have, and which means that the less the more diverse the underlying sort of like base model that we're using is able to generate responses, the better it is. Um, right. So that's part of the trick is like, um, don't use things that are already like to RLHF. They won't take particularly well to this method. Because they've already been sort of like, RL trained for a different set of tasks. And now they're no longer particularly great at this.
Do you remember way back in the day, 2 years ago when the first Mistral model came out, and it had pretty much no RLHF on it, and I think
Yeah,
that's
yeah.
why people loved it so much, was because it was like, "Whoa, we get to do it ourselves? That's amazing."
Yeah, and there's pros and cons of releasing like a model with like no RLHF, but it certainly became really popular in certain subsets of the open source community that wanted to use it for all sorts of like use cases that like a model like Llama was kind of too RLHF to do well on, right? But yeah, so that's kind of the thing to think about here, right? Uh, but well, I guess to this is from like a researchy kinds of perspective. From a customer perspective, they don't really have to think about it because we've already thought about it for them.
Yeah. You've already tested a bunch of different models.
Yeah, we already have a pretty good idea of like the distributions and like which models are spiky, which are not. If they are spiky, how to get rid of some of the spikiness in the distribution such that it's more useful to generate, you know, like a diverse range of things. We've kind of already taken care of this with internal research.
Okay, we've been dancing around this and really talking about how the sausage is made, but what we didn't talk about is the actual results. So maybe you can
Mhm.
give us a quick TLDR of how is this better? In what ways? I guess is the big question that's going through my mind right now.
Yeah, yeah. So the one thing that is, like, super obvious, right? The very obvious, like, baseline is just, like, supervised fine tuning, right? It's like, if you had supervised fine tuning, like, labels, it turns out that it does way better than supervised fine tuning with labels, even though this doesn't have labels, right? That's pretty clear. We tested it on like, like text to SQL, and then like some other benchmarks that we developed that other people in my team have developed previously, which is like the enterprise arena, and we have our own version of like finance bench and whatnot, which test all these sorts of like question answering open and closed book question answering scenarios in very like enterprisey ways. I would never go back to like supervised fine tuning, right? Like it's I think it right. I think it's this is like just way better unless you have like a ridiculously like massive data set of labels that's like rich and whatnot, which like effectively nobody does. Um, And even then, like, Tau is not orthogonal to that. Like, you could still run Tau on top of that,
Oh, nice.
right?
Okay.
Because if you have, like, a label data set with like prompts and responses, guess what you also have? You have the prompts, which is all Tao needs. Um, right. So you can still run like Tao together with the supervised fine tuning step up front. The other interesting thing is that the models are actually like I'm going back and looking at the sort of like exact numbers. But it turns out that like, even the 8B models end up being comparable to like 4.0 for that like like task, right? For that like range of tasks on some tasks, right? Right. So the 8B models, like, if you have a task like finance bench or whatnot, will do as well as like 4.0 or like, O3, like mini or whatever, which are like an order at least, order to two orders of magnitude bigger in parameter count. Now, for the tasks that are like a little bit more complicated, you see like, for like bird SQL or whatever, um, which is more complicated of a task. You see that the performance of like the 8B models are still slightly less than like 4.0 or O3 mini, but that gap narrows and basically vanishes when you get to 7DB.
Oh, nice.
Um, right.
Yeah.
And so this is what I was talking about, is like it's where you are on the sort of like cost quality trade-off, right? What would be good enough for you? And so if you are a person that is doing like financial QA in the line of like finance bench, 8B is probably good enough for you. Right? If you're doing something significantly like more complicated, right, you'd probably need something that's like a little bit like larger sized, um, in order to be able, and like if you're doing something that's like a little bit more complicated and you want to absolutely at like O3 mini level, right? Then you're gonna like need to spend a little bit more
Yeah.
on training it. Um, the interesting thing I will say also is the comparison that we did do. We didn't like show results of like the actual like inference time comparison costs. We kind of just presented them as all equal. But O3 Mini is really doing like test time inference.
Yeah.
Right. They're doing like a lot of like additional compute, whereas like we've baked a lot of that like additional compute in during training time itself. And so like the real correct sort of to speak comparison would be like probably like 4.0 in terms of like test time latencies after the model is deployed. Um yeah. So it's like what's your threshold? How complicated is the task that you're doing? Um, but the results are pretty promising, in the sense that like, with like a 7DB model, even the 7DB is like still like smaller than 4.0 and like O3 MIDI and all of these things. You can erase and basically like get to near parity. Um, and then, well, now you control your fate. Right. To so to speak, right? Like you have this exact model, nobody does anything under the hood that changes like the model behavior. The models don't swap out under the API hood. If like if you give a particular prompt like one day and the model does a certain way, you can build guarantees around that, right? The model's going to continue behaving the same way because you
No
own it.
depreciating a model after a 6-month
No
stint.
depreciating a model. Yeah, like 4.5 is like depreciating already, which is crazy.
Dude, well, this is awesome, man.